So, hello everyone, and welcome to the Frontiers of Parameterized Complexity. I'm very happy to welcome our speaker, Sitan Chen from MIT, who will speak on learning deep ReLU networks that they are fixed parameter tractable. Please, Sitan, the floor is yours.
Thanks so much for the introduction, and thanks for the invitation to speak here. So yeah, I'm really excited to tell you about some joint work with Adam Klivans and Raghu Meka on the question of learning neural networks. And so in the interest of the seminar, I want to spend a few slides to kind of unpack what's often sort of an unspoken connection between parameterized complexity and learning theory. You know, it's pretty uncommon to see the words fixed parameter tractable in papers on learning theory, but actually the kinds of upper and lower bounds we end up showing can very fruitfully be cast in the language of parameterized complexity. So from a lower bound standpoint, many problems in computational learning theory are believed to not be FBT. So some classic questions that you might be familiar with are things like learning, sparse parity with noise, the junta problem, learning decision trees, what have you. I won't formally define what these problems are, but at a high level, these are about trying to figure out, your data essentially depends on some small number of bits of the input, and the number of bits that it depends on is much smaller than the ambient dimension that you're working with. You have some more modern questions like learning mixtures of arbitrary Gaussians, things like learning intersections of half spaces, robust sparse mean estimation with subquadratic samples. So I won't go into details about any of these, but again, the main point is that somehow the widely believed lower bounds for all of these problems look something like the ambient dimension n to some function of the latent sparsity parameter s. Okay. From an upper bound standpoint, we also have a lot of examples of learning problems over nice continuous distributions where you can actually hope for a fixed parameter tractable guarantee. So things like learning mixtures of spherical Gaussians, learning mixtures of linear regressions, neural networks, Gaussian intersections of half spaces, and continuous analogs of juntas. So instead of thinking of the data as sort of depending on some small number of bits of the input, you think of the data as depending on some low dimensional projection of the input. And the thing that you want to be sort of FPT with respect to is the dimension of this low dimensional subspace, which we'll refer to as S. Okay, so I think the main takeaway is really that the kinds of guarantees that learning theorists are often interested in are precisely guarantees that look like some kind of fixed parameter tractable guarantee. And this talk is going to be focused on yet another example in this line of work. In this talk, we're going to talk about neural networks, and we're going to learn them over Gaussian inputs. Okay, so that was just a bit of philosophy. Let me tell you about the outline of this talk. So I'm going to begin with sort of very high level motivation for the specific problem we'll study, and I'll tell you sort of formal definitions to make everything precise. I'm going to then tell you about prior approaches and a very sort of interesting reason why these prior approaches fail. And then I'll tell you about what we show and give you a taste for the techniques. Okay, so let me start with some more philosophical motivation. So at a high level, we're interested in this age-old question of pack learning. So we get a bunch of labeled examples, x, y, drawn from some distribution, and we like to output some function f hat, which you think of as a predictor that achieves low test error with respect to this distribution. I'll make this all formal in the next few slides. But at a high level, if you ask this to a practitioner, they would say, of course, like the right algorithm to run would be to run SGD to train a big and deep neural network on these examples and use that as the predictor. Okay, and this works great in practice. And a central mystery in the theory of deep learning is to understand why this approach seems to work so well, not only from an optimization perspective of being able to fit all of your training examples with a neural network and achieve low training accuracy, but also from the generalization perspective. Once I've essentially perfectly fit my training data, why is it that the resulting neural network can do so well when given examples it hadn't seen? Okay, but apart from asking what's so great about this particular algorithm SGD, you can also ask, a more basic question, which is, how are these distributions over real-world data able to somehow evade these well-known worst-case hardest results for learning neural networks? In other words, for which distributions over data sets can you hope for any algorithm to achieve the above task, let alone SGD? Okay, so questions 1 and 2, they often go hand in hand with each other in terms of the techniques you can hope to use. And at their core, I'd argue they're motivated by a much more ambitious agenda. You could also ask, can we ultimately design better and more principled algorithms for supervised learning? Ideally, ones that come with provable guarantees and that outperform existing techniques on any number of axes like speed, sample efficiency, robustness, etc. Okay, so this is a bit of a pipe dream, but one reason to be optimistic is to look back to what happened with linear optimization, right? When it came to linear programming, back in the day, when Danzig developed the simplex method, this is a great method that works very well on practical instances, even though it was known early on that there exist examples of polytopes for which simplex requires an exponential number of steps to converge for certain choices of pivot rules. And it really took us like 6 decades before the development of things like smooth complexity before we understood why this seems to work so great on practical instances. But even before the development of smooth complexity, we saw the development of interior point methods. And this gave us an entirely new hammer in the algorithmic toolbox for linear optimization. And miraculously, it came with provable guarantees. And nowadays, these are sort of tools which are both widely used in practice in different circumstances. And so you can ask, is there an analog for deep learning? Nowadays, we have this great algorithm of just back propagation and gradient descent. And it works great on real world data, but could we hope for some genuinely new algorithmic idea that could be a sort of peer to SGD when it comes to efficiency? Okay, so that's sort of the high level philosophical motivation for this work. But in order to understand any of these questions, we really have to understand the following more basic question, which is, let's make our lives easier, and let's even assume that the Ys, these labels of my data, actually secretly do come from a neural network. Right? So I'm trying to find a neural network that fits the data, and this is essentially like a promise constraint, saying that there is secretly some neural network that perfectly fits my data. Your goal is just to find it. Okay, so that's all of the high-level motivation. Now let's get into the details. So first of all, what is a neural network? At a high level, you can think of it as just some kind of piecewise linear function. And it's essentially, you take some high-dimensional input vector x, and how it computes the output is as follows. So you take your vector, you left multiply it by some weight matrix, W1, and that's going to give you some vector. And now you're going to apply some entry-wise nonlinearity to this vector. In particular, we're going to work with the standard nonlinearity used in practice, which is the ReLU activation. And this function essentially takes every entry of W1x and applies the following activation to each entry. Okay, so then we get out a new vector. We left multiply it by a new weight matrix. We apply the nonlinearity, et cetera, until at the very end, this final weight matrix WL is just a vector. Okay, so the output is just the inner product between the vector and the vector from the previous layer. And that gives you a scalar output at the end, y. Okay, so at a high level, just think of it as it's really a sequence of matrix multiplications. But in between each matrix multiplication, you stick in this entry-wise function that applies this ReLU, okay, which formally is just the max between 0 and the input. Okay, so let me just introduce some parameters of interest. So we'll call the ambient dimension of the input vector x, we'll call it d, and we'll refer to the number of weight matrices as the depth, L. Okay, the key parameter that we want to be FPT with respect to is the size of the network, and we'll call this S. You should think of this as really the total number of columns across all these weight matrices, W1 transpose to WL transpose. Okay. All right, and then another important parameter will be the effective dimension. So remember I said that all of these works on learning theory that get FPT guarantees, they're secretly about some function that depends on a low dimensional projection of the input. So the parameter k is really the dimensionality of that projection. So it's the rank of this first weight matrix W1, and we'll call it k. Okay. And the point is that f of x is really the exact same as f of the projection of x to the row span of W1, or equivalently the column span of W1 transpose. Okay. And throughout, this is an FBT guarantee, so we should think of this parameter s, which is the size, which is of course an upper bound for this parameter k. We should think of it as much smaller than the ambient dimension d. Okay. And again, this is what we're going to be sort of FBT with respect to. Okay. Does the at this point, I'll pause for any questions about the model. Okay, great. So what do we want to do with these neural networks? Well, the goal is, given labeled examples where the x's come from some possibly known distribution, d sub x, and the y's are generated by this unknown network f, we would like to output some network g, which is close to f in squared loss. In other words, the expectation over x drawn from d sub x of the square difference between the output of the underlying function f and the output of the network you learned should be small. Okay, so this is just the standard like pack learning setup. And we're going to work with a setting, which has been the subject of a lot of works, where you actually know what the distribution over the inputs x is. And it's actually a quite benign distribution. It's just the standard d-dimensional Gaussian. Okay, so that's the setup. That's the data that we get access to. All right, so now let me tell you about what previous works do, because there's been quite a large amount of work in the last 4 or 5 years or so on this problem. So at a high level, all of these works that work with learning neural networks over Gaussian inputs, it's safe to say they focus on the setting where this unknown network f is very low in depth. In particular, it looks something like this. Right, so there are just 2 weight matrices, and you can write the function more compactly as just a linear combination of ReLUs of inner products between the input and some unknown vector wi. Okay, so this is what's called the 2-layer neural network, and all of the techniques can, at a high level, be broken down into the following 3 algorithmic ingredients. So some of the works focus on using spectral or tensor methods via something called Stein's lemma. There are a lot of works on learning neural networks with connections to kernel methods. And of course, there are tons of works on trying to analyze the dynamics of gradient descent with these problems. Okay, so let me emphasize that the kernel methods papers, these primarily work for non-Gaussian inputs where the inputs are bounded in norm by some absolute constant. Okay, whereas sort of the key difficulty in the setup we're considering is that because the inputs are Gaussian, the norms of the inputs really scale with the dimension, square root of the dimension. Okay, what about Stein's lemma and gradient methods? Well, these 2 families of techniques, all of the results in this line of work need to make some manner of assumption about the structure of this unknown network f. Specifically, they'll need to assume some subset of the following properties, either that these coefficients, lambda I, are non-negative, or that the weight vectors wi are essentially nearly orthogonal. And there's actually a good reason for this. And this is a subtlety about the kind of guarantee that you're after when dealing with learning neural networks. So actually, all of these works consider a slightly different recovery guarantee, where they focus not on pack learning, but on something that's called parameter learning. So to motivate what this means, first notice that there are actually different ways of writing down a neural network that would lead to the exact same function. Here's a silly example. The identically 0 function could also be written as just a difference of 2 ReLU activations. And you can come up with somewhat more sophisticated examples where both sides of the equation correspond to different architectures for your neural network, but they really compute the same function. And so in the presence of these kinds of examples, if you really want to work on something like parameter learning, where the goal is to not only recover a network which is close in squared distance to your network, but really close in parameter distance. You really want to know like what exactly are the different weight matrices that constitute this unknown vector, unknown network that you're trying to learn. Then you really do need to make stronger assumptions. Right? You need to make stronger assumptions on the coefficients and on the vectors that ensure that these parameters can actually be uniquely recovered from, let's say, infinitely many samples. So for instance, that's why they need to assume that the WIs are nearly orthogonal or well-conditioned. But when it comes to the more natural goal of actually just trying to pack learn a neural network, none of these assumptions are necessary. Okay, so let me tell you now a bit about what these prior approaches do, because I think it's really important for the, to convey, what's the new algorithmic ingredient that we introduce. Okay, so let me give you a sort of crash course on the spectral or tensor methods. At a high level, they just use the following property about Gaussians. If I take the expectation of y times x, remember y is the scalar label that's output by the network, and x is just the input vector. So expectation of y of x is just some vector. If x is Gaussian, then Stein's lemma tells you that this is nothing more than the expectation of the gradient of the function evaluated at x. Okay? And you can write down what the gradient is based on the functional form for a two-layer network, and it's going to look like some linear combination of these w vectors. Okay, you can go one step further and say, well, instead of y times x, what about y times some matrix function of x? And it turns out this is going to give you something called, this is going to give you the expected Hessian for the network. And again, you can write down what that is. That's going to be some linear combination of rank 1 projectors to these different vectors w. And you can go all the way to the natural tensor analog of this, and it turns out there is some mth order tensor valued function of x called S of m, or the mth score function, such that this expectation on the left-hand side is just the expected mth derivative tensor of the network. And again, you can write this down, and this is going to be some linear combination of tensor powers of the weight vectors w sub I. Remember, these are the columns of the weight matrix W1 transpose at the first layer. Okay, and there is some functional form to this. This is it's some derivative of the density divided by the density itself, but that's not super important. The main thing I want you to take away is that these kinds of ways of interacting with the distribution really involve looking at the expectation between y, the expectation of the product of y, and some function of x. Okay. So why would these kinds of assumptions like the WIs being nearly orthogonal actually help us? Well, if I just took m equals 3 and looked at this third order tensor object, then that's going to be some low rank tensor that I can just run tensor decomposition on. And the point is that because the W's are nearly orthogonal, I can use standard guarantees about tensor decomposition algorithms like Yenrich's algorithm. Okay. On the other hand, if I assume something like the lambda i's, remember these are the coefficients at the output layer. If I assume they were non-negative or positive, it turns out that if I look at the expected Hessian, these coefficients b sub I are going to be positive. And so there aren't going to be cancellations between these rank 1 matrices. In other words, if I looked at the expected Hessian, which we'll call m, this is going to be a sum of rank 1 matrices. In particular, if I take the top k singular subspace of that matrix, I'm going to get back the span of these weight vectors I'm interested in. Okay? And that's going to allow me to sort of get a fixed parameter tractable guarantee, because this will reveal to me the hidden subspace that the function secretly depends on. And it's some some k-dimensional subspace. Once I found that subspace, I can just exhaustively enumerate over it, and that's how I'll get something that's f of k times poly-dimension. Let me mention there's also been some follow-up work that uses more sophisticated variants of this technique involving the mth derivative tensor. Okay, so that's the spectral or tensor methods. But again, the key takeaway you should have is that these all involve expectation of y times a function of x. And it turns out the same picture will be true for gradient descent. So if I write down, a standard gradient step with respect to square loss, okay, the details aren't super important, but the main point is that I have two terms. One, which is just an expectation of a function of x. I know x is a Gaussian, so in principle, I know exactly what this function is, or what this quantity is. The main interesting term is, again, an expectation of the product of y times some function of x. Let me also mention that even for other works that focus on things other than the square loss, they still use updates of this general form. And again, they need to make these kinds of assumptions. So the natural question to ask is, do we need these assumptions if we're interested in pack learning? And it turns out there's a very nice reason why all of these existing approaches sort of got stuck at having to make these assumptions, even for pack learning. And this is something that's called the correlational statistical query variant. The key takeaway, which I sort of beat to death in previous slides, is that all of these algorithms are really, they're using the data in a very specific way. They're saying, they could have been implemented with the following oracle. Instead of actually seeing the samples, they could just have interacted with an oracle that takes as input any function of x, let's say g, and it outputs some noisy estimate of the statistic expectation of y times g of x. Gradient descent and these tensor or spectral methods all fall within this umbrella. And what was shown by two different groups of researchers last year was that if you only make use of the data in this fashion, then you're not going to be able to pack learn arbitrary two-layer ReLU networks, even to constant error, without making d to the size number of queries. Okay, so in other words, there isn't going to be some CSQ algorithm, some algorithm that uses this oracle that can achieve an FPT guarantee. But this begs the obvious question: forget about CSQ algorithms. Even though they capture a lot of natural approaches, can we slightly go beyond this CSQ framework and get an algorithm that actually learns in better than this lower bound? Okay. In particular, at that point, if we have an algorithm that answers this first question, we would like to really go beyond depth 2, because that's really the higher depth is really the practically interesting regime that we care about. Okay, so again, just to summarize, all these techniques, the analysis tends to be quite sophisticated, but at a high level, the key stumbling block is that these techniques only interact with the data via statistics of the form expectation of y times a function of x. Okay, so we're going to go beyond that, and by doing so, we're going to show the following results. Okay, so just as a refresher, here's the definition of a neural network, and the key parameters to keep in mind are the ambient dimension d, the size of the network, which is essentially the number of columns across all of these weight matrices, and the effective dimension, which is the rank of the first matrix. And the effective dimension, again, is the dimension of the subspace that this function secretly depends on. So what do we show? So we show that any neural network, regardless of the depth, which satisfies some weight bound that I'll explain later, can be properly pack learned to error epsilon in time better than what this lower bound tells us. Right, so the details aren't super important. The point is that the sample complexity and runtime are both fixed polynomials in the ambient dimension d times some exponential function of the relevant parameters, namely the effective dimension, the size, this norm bound, and 1 over epsilon. Okay, so this is the first result we show, but actually, you might complain because this norm bound is a product across all of the weight matrices operator norms. And that's going to be, a product of L different things. So really B is, a priori, it's exponentially large in the depth of the network. And as a result, these guarantees are doubly exponentially large in the depth of the network. Okay, so you might hope for better. And with a simple workaround, with an additional assumption, you can actually get significantly better. So let's assume the network is actually Lipschitz. Okay. In that case, B is always going to be a naive upper bound on the Lipschitz parameter lambda. But actually, now you can take these sample complexity and runtime guarantees and essentially replace all the instances of B with lambda with a tiny overhead of a logarithmic term in B. Okay, so again, like the details aren't super important for the main takeaway of this talk. I do want to emphasize that, you know, if you're familiar with this literature on learning neural networks, or like two-layer neural networks, you never see this parameter lambda, and the reason is that if you make no assumptions about the structure of the network, information theoretically, you actually need to see poly lambda number of samples in order to actually learn in general. Okay, so there is some dependence on lambda that's necessary once you drop these standard assumptions that these papers are making. Okay, but the key takeaway is that this is the first example of a neural network class that you can learn efficiently, but provably not by noisy gradient descent. In particular, these lower bounds that I mentioned, the hard instances they construct are, you know, their weight matrices are norm bounded and they are Lipschitz, but you know, this is provably not some kind of bound that you could show using something like gradient descent. Okay, so that's the result. I'll pause for any questions people might have. Great. Okay, so let me tell you a bit about how we show this. So remember, at a high level, the key challenge is to find out what is this low dimensional subspace that your function depends on. Okay, so let's ask a more modest question. Forget about finding this subspace. Let me just find a single direction in the subspace, and hopefully at that point I can hope to make progress. I'll give the subspace a name. I'll call it the relevant subspace. Again, this is just the row span of W1. And the point is that f of x is equal to f of pi u of x, where pi u is the projection to this relevant subspace. Okay, so just to formalize what I mean by this function, depending only on the projection to the subspace. Now, a natural way to try identifying the subspace would be to run this trick from before of looking at the expected Hessian, or expectation of y times xx transpose minus identity. But the key issue is that if you make no assumptions about the network, this matrix can, in some cases, be 0. So it's going to give you no information. So a natural workaround would be, okay, instead of looking at y times this function of x, let's look at some function of y times this function of x. So let's look at this M matrix, expectation of phi of y times xx transpose minus identity for a carefully chosen function phi. And so a basic thing you can show is that actually, regardless of what function phi you pick, the kernel of this matrix is going to contain all of the uninteresting directions. U perp. U perp is just the orthogonal complement of U with respect to this ambient space. Right? And this is a very standard proof. So how do we show this? If I take any uninteresting direction, which is orthogonal to the relevant subspace, V, if I look at the quadratic form of this matrix M evaluated at V, okay, you can write it down. It looks like this. And you know, because the x's come from a standard Gaussian, pi u of x and V inner product x, these are independent random variables. So in particular, I can split up this expectation into a product of expectations. And then you'll notice that this green term, it's just the expectation of a Gaussian of that Gaussian squared minus 1. So that's going to be 0. Okay, so this is a super standard calculation in this literature. And this is really the only place where we need that the inputs are, you know, truly Gaussian. Okay, so this gives us something. It tells us that regardless of what function phi we pick, the main takeaway is that the kernel of this matrix is going to contain the uninteresting directions. And in particular, that tells us that if this matrix were truly non-zero, then whatever, you know, I could take the top eigenvector of this matrix and it's going to be something inside of the relevant subspace just by the contrapositive. Okay, but that's the key challenge. How do I actually show this matrix is non-zero? And more quantitatively, I need to ensure that it's, you know, it has non-negligible energy in the relevant subspace I care about. Okay, so this is just the trace inner product between the matrix and the projector to the relevant subspace. And you can write that down. So it's going to be some expectation. And I just want to emphasize that the key technical obstacle is this minus k term. In some sense, to ensure that this inner product is non-zero, I want to really fight against the cancellations that get introduced by this minus k term. Okay, so how do we go about analyzing this inner product? How do we show that this matrix is actually non-zero for some appropriate choice of phi? Well, let's play the following thought experiment. Let's see what I actually need in my function phi for this to work. So let's imagine that phi satisfied the following properties so that it ends up looking something like this function here. First of all, I want it to be non-negative, and I want it to, of course, not be identically 0 over f of x. So that's just to ensure that this thing inside the expectation isn't always 0. So these are very natural things to want. The most interesting constraint we would like phi to satisfy is the following. Imagine that it also satisfied the property that it's non-zero on f of x if and only if the norm of the projection of x to the relevant subspace is large. So in pictures, what this looks like is if I plot on the x-axis the norm of the projection to the relevant subspace, and on the y-axis I plot the value of phi over f of x, I want to ensure that this function basically stays 0 up to a certain point, and then past that point, maybe it becomes non-zero. So why does this help us? In particular, what is the point of this third constraint? So let's do this out very slowly. So the inner product at the very top, I can break up into two events. I can break it up into the scenario where x has, the projection of x has small norm, and the scenario where it has big norm. So I've just split it up into these two complementary indicators. And now the key point of property 3 is that if x falls into the second event, when the norm of the projection is small, then by the contrapositive of 3, phi of f of x is going to be 0. So the second term completely goes away, and we're just left with the first term. And now property 3 tells me that, or the fact that I'm restricting to things which have norm at least 2k means that this quantity, which is the norm minus k, is going to be at least k. Okay, 2k minus k. Okay, so in that case, I can rewrite the expectation as the following. And because I assumed that phi of f of x is not identically 0, and it's non-negative everywhere, this entire expectation is going to be positive. Okay. So this is all telling me that if I could find a phi which satisfied these three properties, then if I just took the top eigenvector of this matrix M that I defined earlier, then I would be able to find a direction in the relevant subspace. Okay, so the key challenge is how do I pick this phi to satisfy these three properties? And I claim that a very simple choice of phi actually works. Let's take phi to be a threshold function. So phi is just the indicator for whether the input has absolute value exceeding some threshold tau, and tau we're going to pick to be lambda times root 2k, where lambda is this Lipschitz parameter and k is the effective dimension. So I'm going to justify all of this shortly. Let me just mention that this is also reminiscent of existing techniques in non-parametric regression called sliced inverse regression. And actually we use it in this result that I flashed briefly at the beginning of the talk to learn polynomials that only depend on bounded dimensional projection of the input. Okay, so in the previous picture I said we want phi to look something like this. The wavy thing that you see at the end of this curve isn't super important, because once I take phi of z to be the indicator for this absolute value exceeding tau, this is the plot that we get. Okay. So why would this help us? So let's recall this lower bound that we had from the previous slide. This is the lower bound on the inner product between M and the projection to the relevant subspace. I can first bring out the k. Okay, nothing interesting going on there. But now the point is that because of property 3, I can write this expectation in a very natural way. The point is that phi of f of x is non-zero, namely this absolute value of f of x is at least tau, only if the norm of the projection is large. And so in other words, it's just going to be equal to the expectation of the indicator that phi of f of x is non-zero. In other words, the indicator that f of x exceeds this threshold in absolute value. And the expectation of indicator is just a probability. So really what we want to show is non-negligible is the probability that this function is large in absolute value over a Gaussian input x. At a high level, what is going on in this algorithm? When I take this choice of phi, the idea is, I would like to somehow do some kind of principal component analysis of my data. But instead of doing it over the full data set, I'm taking only the points x comma y in my data set where y is sufficiently large in absolute value. I'm just going to do PCA over those points. So that's the sort of full algorithm idea for this part of the talk. Now, how do you analyze, why would it be reasonable to be able to pick this choice of tau and get properties 1 through 3? Here's a picture. So somehow this red circle is really the region that we want to avoid. This is where all the annoying cancellations take place. So I just need to pick a choice of threshold. Let me take a step back. So this figure that I'm showing you is the heat map for a neural network in 2 dimensions. Okay. And so you can think of these different colors as different possible choices of tau I could pick. They're the sort of level sets of the function. So as long as I pick tau to, for instance, cover this dark blue region in the middle, then if I condition out all of the data which falls within that dark blue region, I'm left with this purple region. And this purple region's volume with respect to the Gaussian is exactly this probability that we want to lower bound. Okay, so this is just to convince you that there is actually a very natural choice of, it's not inconceivable that there should be some choice of tau for which properties 1 through 3 will work. But let me convince you why this particular choice is a good candidate. So tau equals lambda times root 2k. Okay, so let's try verifying this important third property, that phi of f of x is non-zero only if the norm of the projection is large. So let's prove the contrapositive. If the norm of the projection were small, if it were less than 2k, I claim that the function is actually going to be smaller than this threshold of tau that we defined, lambda times root 2k. Okay. So first of all, just by definition of relevant subspace, f of x is equal to f of pi u of x, so their absolute values are the same. And now I'm going to use Lipschitzness. So f of pi u of x is at most f of 0 in absolute value, plus Lipschitz parameter times pi u of x in norm. Okay, this is just using Lipschitzness. Now f of 0 is just 0, right? This is a homogeneous function. And furthermore, the norm of pi u of x is at most square root of 2k, just by assumption. Okay, so this is at most lambda times root 2k. So we've proven the contrapositive. Okay, and now I just have to convince you that this function isn't identically 0. But remember, I need a quantitative version of this if I want to be able to get finite sample guarantees. So I need to show that the probability that the function takes on a value bigger than tau in absolute value is non-negligible. And this is effectively to try to show anti-concentration for this piecewise linear function f. So here's like a sketch of the proof. The idea is we're going to heavily exploit the fact that f is a piecewise linear function. So we can assume without loss of generality that the variance of this function is sufficiently large. Otherwise, this function is close to 0. So I could just output the 0 function, and that would be a pack learning algorithm. So assuming that the variance of the function is non-negligible, then on average, if I pick a random linear piece of f, one of these cells that you can see traced out by these white lines, the conditional distribution over that cell for this function is going to have non-negligible variance, and therefore some level of anti-concentration. If random variable has sufficiently large variance, it should be able to exceed a certain threshold some fraction of the time. So if I focus on this particular linear piece of the function, it turns out you can lower bound the probability that it exceeds this threshold tau by some convex function of the variance. And then at that point, I can just use Jensen's and law of total variance. Right? So that's just a sketch for why you should expect there to be a non-negligible fraction of the mass inside this region where f of x exceeds the threshold. Okay, so what have we achieved? In math, it looks like this, but at a high level, what this is saying is that if I form this matrix M, which is essentially taking phi of f of x to be the indicator that absolute value of f of x exceeds tau, if I form this matrix and I take its top eigenvalue, it's going to be non-zero. So this matrix is really, it's not 0. And that means that if I can always estimate this matrix by drawing enough samples and looking at the top eigenvector. And that top eigenvector, the key takeaway is that it actually lies inside of this relevant subspace. Okay? From a finite number of samples, it's going to be close to the relevant subspace. Okay, but at this point we've made progress. We figured out at least one vector inside of this U, the subspace U. Now you could be more ambitious and ask, maybe the full spectrum of the matrix is going to reveal the subspace U. Empirically, it seems like this isn't the case. So you actually need new ideas to go further. So now the key question is, how do I actually learn the rest of this subspace? Okay. And the punchline is it's going to be a very similar analysis to what we saw with one key trick. Okay, so to recap, we found some vector inside the relevant subspace, call it V. And we want to find now another vector inside of the subspace. And of course, I want it to be orthogonal to what I found so far. So here's the matrix we worked with earlier. One way to encourage our algorithm to find something that's orthogonal to V would be to add orthogonal projectors on left and right. Okay, but this is silly because if I could analyze this matrix, I could have just analyzed the matrix without projectors. So we need to crucially modify what's in the middle in some way. And we'll focus on what we're actually thresholding on. So remember, before I said, we're basically doing PCA, but we're throwing out all of the XY pairs where Y is too small in absolute value. Well, now we're going to do something different. We're going to throw out XY pairs where the following quantity is too small in value. The absolute value between Y and the absolute value of Y minus F of pi Vx. You can think of this as kind of the difference between the true label and the label generated by the network we've learned so far. So F of pi Vx is you take the input and you first project it to the direction we found so far, and then you run it through this unknown network. Okay. But of course, there's one key issue is I don't know what F is. So I could never hope to actually form this matrix. So there's a bit of a chicken egg problem here, but I'll say later how to address this. It turns out using the same argument as before, you can say that the kernel of this matrix contains all of the uninteresting directions. It's going to contain, the orthogonal complement to the subspace we actually care about. It's also going to contain the span of V simply because we added projectors, orthogonal projectors to left and right. But really the hard part, again, is to show that this matrix is non-zero, in particular to show that it has non-negligible energy inside of the subspace we care about, which is now the relevant directions, U, that are orthogonal to the direction we found so far, V. Okay, so how do we do this? We can still write down this inner product as before. It looks something like this. Now, how do we analyze this? So what did we do before? Before, we wrote down the inner product and we wanted to check sort of two key properties. One is that the probability that the absolute value of Y is large. And the second key crucial property, which says that the absolute value of Y is large only if the norm of the projection of X is large. Okay, so now let's start pattern matching. Like, how do I hope to get the next relevant directions? Well, remember, now we're not thresholding on absolute value of Y. We're thresholding on this residual quantity, absolute value of Y minus F of pi V of X. And we're not projecting to U, we're projecting to the remaining directions inside of U. Okay, so that was what I wrote on the previous slide. And now let's try percolating all these changes into the green box. I don't want to check that the absolute value of Y is large, or the probability that the absolute value of Y is large is non-negligible. I want that the probability that the absolute value of the residual is large. Okay, and similarly, I'm going to replace this absolute value of Y here with absolute value of Y minus F pi V of X. And again, I'm interested in the projection to the remaining direction, so U minus the span of the direction we found so far. And I'm interested only in X, which are orthogonal to V, because remember, I put these orthogonal projectors on left and right. Okay, so this was purely pattern matching. Like if this went a bit too quickly, because I'm running a bit low on time. Yeah, don't worry. Like the key point is that you should the key move is to really condition on data for which absolute value of Y minus F pi V of X is large. And once you do that, somehow the rest of the analysis is really just pattern matching what I told you from before. Okay, so let's percolate this further. Okay, we can change all the elements of the previous proof in the natural way, and we'd be done. So if we can satisfy properties 1 and 2, we'd be happy. How do we satisfy properties 1 and 2? And I claim that the analysis is exactly how we satisfied properties 1 and 2 from the previous slides. Okay, so let's say I want to show that the absolute value of this difference, y minus f pi v of x, is large only if the norm of the projection is large. Well, let's take any x which is orthogonal to v, and let's just try proving the contrapositive. So if the norm of its projection were small, I want to show that absolute value of y, or f of x, minus f of pi v of x is small. Okay, so I can use Lipschitzness again, and it's just a, essentially a 3-line proof. So f of x minus f pi v of x. Remember, f of x is just the same as f of pi u of x, right? It only depends on the projection to u. Now I use Lipschitzness. So the difference between pi u of x and pi v of x is just the projection of x to u minus v. Okay, so again, I'm just using Lipschitzness. And now I'm just using the assumption that the norm of the projection is small to say that this is at most lambda times the square root of 2k minus 2. So if I took tau to be lambda times root 2k minus 2, oops, I would get property 2. So nothing new has been done except sort of pattern match absolute value of y into absolute value of the difference. Okay, and similarly, if I look at this property, probability that the absolute value of the residual is large is non-negligible. Again, I need to show anti-concentration of some piecewise linear function. So 2 things could happen. One is that the variance of this residual function, y minus f of pi v of x, is large. Then I can just run through this, this convexity argument I had earlier. The point is that f of x minus f of pi v of x, it's also piecewise linear. So I can just apply the exact same argument. On the other hand, if the variance is small, then I claim we're already done. The point is that this means that f of pi v of x is already close to the underlying network. So we can just output this network f of pi v of x. Okay, so that gives the full analysis. And what's the takeaway? In general, I can iterate this whole argument that I just described and learn more and more directions. Let's say the directions I found so far span some subspace V. The point is I can now form this matrix that I defined earlier. I'm thresholding on the absolute value of the difference of between the true label and the network we've learned so far. I'm adding orthogonal projectors to left and right. And this matrix is going to be non-zero. And in particular, if I estimate this matrix from samples and I take the top eigenvector, that's going to recover a new direction inside of my relevant subspace. And I'm going to make more progress. Okay, so there's just one more thing I owe you, which is, of course, you can't actually form this matrix M prime. And the reason is that it depends on F, which is the network we're trying to learn to begin with. So how do we fix this? Okay, so here's the key trick. We don't have access to it, but we know the subspace it depends on. We know that it's V, which is the span of the directions we found so far. And particularly, we know that that F is a bounded size neural network. Okay, so we can simply exhaustively enumerate over all possible networks to a fine enough granularity. So we're going to construct a net over neural networks, and we're just going to try different guesses for what f of pi v of x actually is. There's also another technicality that needs to be addressed, which is, of course, because we're only drawing a finite number of samples, we're only going to ever get approximations to these matrices that we're taking top eigenvectors of. And so the eigenvectors we output, they're not going to lie exactly in this true subspace we're working with. They're only going to be close. Okay, and so the key technical hurdle that needs to be overcome is, is this entire analysis actually stable to this kind of finite sample error that we introduce? Okay, so the key part of the analysis is the following. We need to understand stability of affine thresholds of ReLU networks. And I want to say in pictures what that means. So here's the key stability result. what do I mean by an affine threshold of a ReLU network? So let's return to this heat map for a two-dimensional neural network. The point is, if I take this neural network and I slightly tweak the weight matrices, the underlying parameters of the network, maybe I'll get something slightly different, right? As I go between these two choices of parameters, the heat map slightly changes. Now, the key thing I want to upper bound in pictures is the following. Let's look at, I'll overlay these two heat maps. And what I want to upper bound is this kind of light purple sliver that marks the region of disagreement between these dark blue regions of the heat maps. Okay, so in math, what this means is very simple. I have two neural networks, and they're almost the same in parameters, but they're exactly the same in terms of the dimensions of the different weight matrices. So they have the exact same architecture, but the weight matrices are slightly off. They're alpha close and operator normal. What I want to upper bound is the probability, for a fixed threshold tau, that one network exceeds tau in absolute value, and the other network is at most tau in absolute value. Okay, that's what I mean by this area of disagreement between those two heat maps we saw earlier. And what we show is that this is upper bounded by some linear function in alpha. I want to emphasize that this is, you can think of this as kind of like Shepard's lemma, but an affine version. And instead of linear functions, you're working with deep neural networks. And remember, this parameter B is just the product of the weight matrices for the underlying network. So how should I think of alpha in the, if I actually try plugging this lemma into our analysis, you should think of alpha as kind of like the granularity of this net over neural networks that we created, that we were exhaustively enumerating over. And it turns out it also scales with sort of the level of approximation we can get to the relevant subspace. So as we learn these different directions, V1 through Vm, over the course of iterating the spectral algorithm I told you about, the span of all these directions is going to be essentially alpha close to U in some notion of subspace distance. Let me emphasize that the linear dependence on alpha is actually crucial. It turns out if you had a bound which was slightly worse than alpha, maybe like alpha to the 0.99, this would actually give you sample complexity which is doubly exponential in the effective dimension. Just a technical point. Okay, so let me say a bit about how to prove this, Shepard's lemma for neural networks. And the key idea, which if you take nothing else from this talk, I think the following fact is a very nice fact that should be more broadly useful. And this is just that any continuous piecewise linear function can be expressed in a very simple way, essentially as a CNF of linear functions. Right? So at the leaves, we have n different linear functions. And you should think of these linear functions as the linear functions in the different pieces of the piecewise linear function. And the claim is that there is always some choice of clause structure such that you can write this function as a max of mins of these different terms. Okay, so you can think of it as just like a CNF, but instead of ors of ands, it's really maxes of mins. Okay, so how do we use this? The key point that this theorem tells us is that instead of talking about arbitrarily deep neural networks, we can kind of compress the depth of the network down to this finite depth object, which is just this depth 2 like lattice polynomial. And this will allow us to prove this key stability result. The basic idea is a hybrid argument. Let's take the two max-min formulas for our two different neural networks that are close in parameter distance. It turns out you can open up the black box of this theorem that I mentioned earlier so that you can actually ensure that these two networks, because they have the same architecture, the resulting max-min formulas actually have the same architecture as well. So they have the same clause structure. At this point, let's implement the hybrid argument. So we're going to consider a sequence of hybrids between phi and phi prime, where I slowly swap out functions at the leaves. So I swap out the first leaf, I get phi 1, the second leaf, I get phi 2, and eventually I swap out and I get back phi prime. So that's the sequence of hybrids we'll work with. And it turns out if I want, I just want to compare the probability that two adjacent hybrids disagree with respect to this affine threshold function. So instead of considering the probability that f and f prime disagree with respect to this threshold, I just need to do a union bound over the different pairs of successive hybrids. It turns out comparing a successive pair of hybrids actually reduces to comparing two different linear threshold functions. And those linear threshold functions are precisely the two different leaves present in those two hybrids. So one was the original leaf that belonged to the function phi, and the other was the leaf that got swapped in during the hybrid argument. Okay, and this is just some elementary fact about stability of affine linear thresholds. This is something you can prove, and that's where you get this linear dependence on alpha. Okay, so let me, so that's the full algorithm. I'll kind of speed through it, and I'll tell you about open questions. So at a high level, we're maintaining a list of different relevant directions. So this list starts out as empty. Every step, let's say we found directions which span a subspace V, and then we just enumerate over networks that are over this subspace V. If I find a network that achieves low square loss, I'm already done. I just output it. Otherwise, I'm going to run through the spectral algorithm that I described earlier. I'm going to form this matrix. And if this matrix is non-zero, I'm going to output the top eigenvector. I'm going to add that to my list. I'm going to recurse, or I'm going to repeat. And eventually, as I repeat and I accumulate more and more vectors, at some point, I've learned enough vectors that this net over neural networks is going to contain a good function f. And at that point, I will find that function in the course of brute forcing. I'm just going to output that function. And then I'm done. So that's the full algorithm. Okay, so let me conclude very briefly with a summary and some open questions. So what do? We circumvented the CSQ barrier I described earlier by using fundamentally non-CSQ statistics of the following form. And this gave us the first efficient algorithm for learning general ReLU networks of arbitrary depth in a regime where gradient descent couldn't. Let me just conclude with some open questions. There are a lot of interesting technical directions to improve upon. One interesting one is to go beyond this Gaussianity assumption and try to see what are distributional properties of real world data that can make this problem even more tractable. I think it's also an interesting direction to see, can you actually try running this algorithm? The analysis is pretty pessimistic when it comes to how big you have to pick this threshold for throwing out points, but you could hope that maybe with more modest choices, it could already be useful for identifying the relevant subspace. Okay, so that's all I wanted to talk about. Happy to take questions now. Thanks.
Yeah. Thank you very much, first of all. Yes, please. Time for questions, indeed. Well, it could mean only that the talk was very clear and everyone understood everything, right? So yeah. so thank you very much, Sitan, once again for coming and to speaking.
Yeah, thanks for the invite. Yeah.
Yes, thank you. Bye.
See you all.
Bye.